Good morning, everybody. So it's a pleasure to have Benoit with us, starting this session, talking about the variation formulation of the histine system.
Thanks very much. Thank you, first of all, the organizers for the invitation. It's great to be back in Stockholm 3 weeks after giving roughly the same talk. So I apologize to those who have seen the talk before. There'll be some slight differences, so you can guess the difference. So the object of the talk is to talk about a paper which has now come out, which is this paper that came out on Monday last week with my co-authors Vincent Cordrelli, who's in the audience, Derek Howland and Anup Singh. So to start, let me start by motivating the context of this work. So we worked in this general framework that was first discovered by Costello, Whitten, and Yamazaki, which relates d-dimensional integrable field theories on some manifold n and some high-dimensional d plus 2-dimensional gauge theory on the manifold n cross the Riemann surface, which is partly topological, partly holomorphic. So you can understand this kind of correspondence fairly intuitively by the fact that most integrable field theories are described by a lax connection, and the lax connection depends meromorphically on some spectral parameter. So what the gauge theory does is it incorporates this spectral parameter as part of the geometry. That's where this cross with the Riemann surface comes from. And the idea is that the gauge field of the gauge theory becomes the lax connection of the integrable field theory. So there's been lots of examples of this kind of picture over the past few years in higher dimensions as well. So it started off in 4 dimensions relating it to 2D integrable field theories. That was the original work of Costello and Yamazaki. Most of the work has been done on CP1 and also very interesting work on on elliptic curves in the 4D case. And in high genus, it's been limited mostly to the Riemann surface so far, the Riemann sphere. So I'm not going to talk about these high-dimensional settings in this talk. What I'm going to do is go one dimension down and focus on the simpler setting of what's called 3D mixed BF theory, which is living on R across the Riemann surface. And the reason I do that is because it's, well, somehow very rich because it's related to the Hitchin system, which can be defined on an arbitrary Riemann surface. And so in particular, I'll show you that you can really connect these two theories really for an arbitrary Riemann surface, as opposed to these high-dimensional cases, which for the moment are only understood in lower genus, 0 and 1. So the purpose of this talk is, moreover, to describe the fact, to use the fact that the Hitchin system is a complete integrable system, and to give a Lagrangian formulation of that complete integrable system. So I'll explain what that means in a second, and explain how this works in arbitrary genus. Okay. So I'm really going to explain how you can go back and forth between the Hitchin system and the 3DBF theory. So I'll derive the 3DBF theory as a Lagrangian formulation of the Hitchin system in particular. Whereas usually the correspondence is always going this way. You start from the gauge theory and you extract from it some integrable field theory. Okay, so let me start by something everyone is familiar with here. So recalling what an integrable system is in finite dimensions. So we have a phase space, T star m, a Hamiltonian on this phase space. This Hamiltonian describes a completely integrable system if you can find n integrals of motion. So the n is the dimension of the manifold M. These should be integrals of motion, or they should Poisson commute with the Hamiltonian itself. They should be in involution. This is a crucial property, which essentially means that all the time flows, the time flows under all the Hamiltonians preserve the other Hamiltonians. So in particular, what this means is you can restrict the level surfaces where all the Hamiltonians are constant. So these are the Liouville tori in the phase space, and the dynamics happens on this Liouville torus, and you can solve it in terms of action angle variables. So this is a crucial property which will come up again shortly. And you also require that the Hamiltonians are functionally independent, which you can describe by saying that the differentials are linearly independent at any point on the cotangent bundle. Okay, so of course there's always an obvious integral of motion, which is the Hamiltonian itself. But the crucial thing to note is that properties 2 and 3 here are actually symmetric under the exchanges of all the Hamiltonians. So it's very natural to treat all the Hamiltonians on an equal footing and not just treat H1 as preferred. So in this case, we talk about an integrable hierarchy where all the individual Hamiltonians each generates an integrable system of their own, for which the other Hamiltonians are the integrals of motion. So this is the concept of an integrable hierarchy. And what I want to do today, and you'll hear a lot more about it tomorrow from Vincent, is how to formulate this notion of integrable hierarchy from a Lagrangian point of view. and I'll do it specifically in this talk on the Hitchin system. So let me remind you about this framework, which was initially developed by Loeb and Nijhoff in 2009 on what are called discrete integrable systems with discrete time. But this has been generalized, as Vicedo explained, to many more integrable models. So to motivate it, let me start with just an individual time flow for time ti. So on the phase space, this is given by these Hamiltonian equations. And we know that we can encode these equations for a given time ti in terms of this Lagrangian, the first order Lagrangian. And what it is, it's a Lagrangian for a curve, so a map from R to the cotangent bundle. So yeah, one parameter family of points on this cotangent bundle. And the action, which is the integral of this Lagrangian, with respect to that particular time ti, if you vary it, you get back the Hamiltonian equations. Okay, so this only describes one particular time flow. And the question is, well, how do you describe all the time flows together in one Lagrangian? And more importantly, how do you encode the involution property of these Hamiltonians, which is crucial for integrability in the Lagrangian framework? Okay. So this is where multiforms come in. So the key idea, which goes back to Loeb and Nijhoff and has been developed by many people since then, including Vincent, who's an expert in the audience, is to introduce the notion of Lagrangian multiform. And I'll focus in this talk on Lagrangian one forms, which are appropriate for finite dimensional systems. The one form means there's one time. Okay. So you take this Lagrangian one form, and I'll also focus on a formulation which is very recent by Caudrelier and Harland, which is essentially equivalent, or they showed it's equivalent in their paper to the original formulation, but it's a bit cleaner, so I'll focus on this presentation. So what they did was just extend the phase space by n dimensions, Rn. So you look at this Lagrangian one form on this phase space, so it's really a one form. So PDQ minus Hamiltonians dt. Whereas before I had no sum over I, now I'm explicitly summing. I have implicit summation convention. So here I've included all the times as part of the Lagrangian. So because I want to describe the dependence of these points P and Q on all the times, I don't want just to consider a curve in phase space. I want to consider an n-dimensional surface in phase space. So the P's and Q's will depend on n different times. So I should describe the surface in that phase space. So the dynamical degrees of freedom now are a map from Rn, this is a multi-time space, into the phase space. So the technical thing here is just I'm just adding this Rn in the codomain. It's not really necessary to do that, but it's cleaner to do it. Okay, so this is the kind of map we want to describe variationally. And the point is that if you take this Lagrangian one form on this cotangent bundle and you pull it back to Rn, you get a one form on Rn. But you can't integrate a one form on Rn, so you need a curve in Rn to be able to write down an action. Okay, so you just pick an arbitrary curve from 0, 1 to Rn, so trace out a curve in Rn, and you pull back the Lagrangian to that curve. And then you can integrate it. Okay, so this is the action formulation for the multi-time system. So the point is it's a one parameter family of actions for this dynamical degrees of freedom sigma. Okay. And so now the question is, when you vary it, what do you get? So you have to vary this family of actions for all gamma with respect to the dynamical degrees of freedom, which are encoded in this map sigma. Okay? So remember, sigma includes not just the p's and the q's, but also t. So if I vary the action with respect to p, q, and t, the first two equations look like the Hamiltonian equations for different times. And then the last one looks interestingly like the involution property of the different Hamiltonians. In particular, if you plug in the first two equations into this last one, you get precisely the Poisson bracket of hi with hj times this matrix, dti by duj. So if we were to be able to invert this matrix, we would have the involution property. And it turns out that this is invertible because I should have said, I'm assuming this is an immersion, meaning that it's locally an embedding of Rn. So it's got an injective differential. And what that means is that by the first two equations, if this matrix was not invertible, neither would dq mu by duj be, and neither would dp mu by duj. So that means that if this map was not invertible, this differential would not be injective, and so I wouldn't have an immersion. So I can in fact invert this matrix because I'm assuming sigma is an immersion. So that means that I have the involution property. And moreover, if I invert this matrix here, I get the usual Hamilton equations for every single time of the hierarchy. Okay, so I get from this action principle, I get all the Hamilton equations for every single time flow and the involution property of the Hamilton. Okay. So you'll hear more about this kind of setup tomorrow from Vincent. One thing we did in this paper is generalize this story to gauge systems. So what that allows us to do, yeah, go on.
So then this n is the number of conserved quantities or the number of degrees of freedom of the system?
It's both in this case, because I'm interested in integrable systems. You could make it different to the total number of degrees of freedom, then you'd have not an integrable system, but
No,
Yeah.
that wasn't what I was going to ask.
okay.
I was just going to say, so when we go to field theory, you're going to take that to infinity.
I'm not going to go to field theory
Okay,
because that's why I'm looking at the Hitchin system today.
I see.
It's a finite dimensional integrable system. Yeah, but that's a great question. What do you do in the field theory case? Yeah. So I'm going to be interested in describing the Hitchin system as a symplectic reduction, as it's usually done. So what we did in this paper was generalize this Lagrangian one-form framework to gauge Lagrangian one-form. So let's think about a group G acting on the cotangent bundle, and let's suppose that it's acting in a Hamiltonian way with this moment map. Okay, and I'm going to assume that the moment map is preserved by all the time flow. So this is really a symmetry of the system. Okay. So what I want to do is implement Hamiltonian reduction to this symplectic quotient, level 0 of mu, quotiented by the residual action of the group G. And there's a very simple way to implement this in the Lagrangian. First of all, the restriction for the level set mu equals 0, you just implement by adding a Lagrange multiplier times the constraint mu. So A here is a G-valued field, or G-valued one-form on Rn. I pair it with the moment map, which is pulled back to this multi-time space Rn. And this is just a one-form valued in R or in C. And so I can add it to the Lagrangian, and this will, by design, encodes the equation of motion mu equals 0 through the variation with respect to A. The other thing I want to do is pass to the quotient. And the point is that once you've added this Lagrange multiplier, you notice that the original global symmetry gets promoted to a local symmetry. Namely, the action with this extra term is now invariant under this local symmetry. So I can act with the original transformation on the field sigma, but pointwise at every point u. And I let the Lagrange multiplier transform as a gauge connection. Okay. So the key point here, takeaway, is that in this Lagrangian formulation of gauge theories, the Lagrange multiplier, which implements the restriction to the level set mu equal to 0, becomes a gauge field along Rn. Okay. Rn being the different time direction. Okay. Yeah.
Should I think of this as being equivalent to gauging like a space-time symmetry, like a map from space-time to the group, or?
Yeah, this is effectively the space-time, but it's a multi-time space, so it's really one-dimensional systems, but there are many of them, which you're treating as a collection of systems. It's really this multi-form language for individual integrable systems with one time, but they're together in one Lagrangian. Yeah. So it's not really a field theory, although the 3dBF theory will be a field theory on this place. Okay, so when we vary the action with respect to the different variables, now we have to vary with respect to A as well. And so we get this constraint, mu equal to 0. And the equations of motion for P and Q are, you recognize them as the Hamiltonian equations of motion for a constrained Hamiltonian system, where you not only evolve by the Hamiltonian for each time, but also by a arbitrary time-dependent function or multiplying the constraints. So this is just saying that at every point in time, you're allowed to do a gauge transformation along the flow. Right? So this is just the usual Hamiltonian for a constrained Hamiltonian system where you add the constraints to the Hamiltonian. And again, because of the setup, when we vary with respect to t, you get again the commutativity of the Hamiltonian. And remember that to get the Hamiltonian equations of motion, I really have to invert this matrix dt I by duj. I do this again here, and so I've done it explicitly from the start. So this field A is really like the pullback of the one form which was on the U space to the T space. So it's just a one form transformation here from the U's to the T's. Okay, and then the other crucial thing is that if the action of the group G is free, which will be the case later, then for free I get the fact that these gauge fields actually form a flat connection on Rn. So this will be an important fact later. Okay, any questions so far? So now I want to move on to the Hitchin system. So So the Hitchin system is a completely integrable system. So it's the setup I've talked about just now, until now, but it's on a very particular general phase space. So pick a Riemann surface C of genus G greater than 2 for this talk, but we can also deal with the cases G0 and 1. They're just very generic or degenerate. So for simplicity and for uniformity in this talk, I look at just genus 2 or higher. So the Hitchin phase space is this cotangent bundle of the space of isomorphism classes of stable holomorphic principal bundles. So I'll spend a bit of time explaining what those words mean. One thing to say is that stable is a very technical condition. I don't want to enter into it in this talk. You can ask me questions about it later. But it's just a condition that will be sort of useful at some point. I'll explain where it comes in. But so what I want to explain is, well, because this will be very crucial for what follows, is what do I mean by holomorphic principal bundle, and what is an isomorphism class of such things. So the nice thing is that this phase space, first of all, this bundle GEC, this space of isomorphism classes, is finite dimensional, and the cotangent bundle is also finite dimensional. So the phase space has this dimension. So keep this number in mind, 2 times G minus 1 dimension of G. This is again only for G greater than 2. So a holomorphic principal bundle, you can think of it simply as a principal bundle, but whose transition functions are holomorphic functions. So a principal bundle is described by transition functions on overlaps of different charts. Okay, so it's a G-valued function on the intersection of 2 charts. And it has to be holomorphic if you want the principal bundle to be holomorphic. So that means that the del bar of this Gij is 0. Okay. And the isomorphism class of such things is just you treat 2 holomorphic principal bundle whose transition functions are related by this conjugation with a HI defined individually on each patch. So if 2 transition functions are related in this way for every pair of patches, then the 2 corresponding principal bundles are called isomorphic. And the reason is because this transformation is basically just a change of local trivialization. So you don't want to distinguish 2 principal bundles described in a different local trivialization. Okay. So what's the cotangent bundle of this space? So if you pick a isomorphism class of a holomorphic principal bundle, the cotangent space is described by what are called Higgs fields. And in this case, they are holomorphic Higgs fields. So what this means technically is just that I have 1-0 forms, which are holomorphic on every patch. So on every patch, my Higgs field is described by a 1-0 form holomorphic in that coordinate. Okay. And across 2 different patches, they are related by the coadjoint action of the transition functions, because I should have said these are 1-0 forms valued in the dual of the Lie algebra. Okay, so on every patch, you have a G star valued 1-0 form, which is holomorphic. And across different patches, they connect together by this adjoint action. Okay. And the components are all holomorphic in every coordinate locally. Okay, so what are the Hamiltonians of the Hitchin system? So this is a beautiful construction due to Hitchin. So you pick a basis of G-invariant homogeneous polynomials. Okay, so these are labeled by the 1 to the rank. And their degrees as homogeneous polynomials are the exponents of the Lie algebra plus 1. So the map is the following. What it's defined as is it's defined on every fiber. So what you do is you pick what you do to the Higgs field on that fiber is you apply the polynomials to that Higgs field. Okay, so you get some collection of sections of different bundles. So because these polynomials have degrees, the exponents of the Lie algebra plus 1, the exponents of these numbers dr. So if you apply a polynomial to a G star valued 1-0 form, if the polynomial has degree dr plus 1, you get back a 1-0 form tensor dr plus 1 times with itself. Okay, so these are sections of these line bundles. And so the point is that these line bundles have a space of holomorphic sections, which is this particular expression. And the remarkable fact is if you add up all these dimensions, it's exactly half the dimension of the phase space. So what this map does is it defines for you a collection of n independent Hamiltonians, n being half the dimension of the phase space. So it's a complete set of Hamiltonians, which for reasons I don't want to go into here are in involution and have all the properties of an integrable system. I'm just showing you here the count is correct. Okay. Any questions about this? Yeah.
How should I think of this B? Like a small change in the connection or something, or?
It's a dual to connection. It pairs with connections because it's G star valued. So, and it's also, connection is a 0-1 form, this is a 1-0 form. So the reason is, that's a natural description of the cotangent bundle of the fiber of that is because the connections parameterize the base, if you like, and the fiber is the dual to that. Yeah. So, yeah.
What's the symplectic structure on it?
I haven't written it down, you'll see it later. It just comes out in the action, but the point is I'll move to a different description of the Hitchin system as a reduction of a bigger space, infinite dimensional space, but this is the sort of the description we want to land on. This is the honest to God Hitchin system with this phase space with some symplectic structure I'm not writing down because it's a bit fiddly to write, and it's not really important at this stage. Yeah. Okay. So that's the system I want to describe. So as I said, I want to view this as a symplectic reduction of a much bigger system, which is infinite dimensional. So the point is that there's another way to think about holomorphic principal bundles, which is to start with a fixed smooth principal bundle. Okay, so now I'm working really with smooth things, and all this story I talked about with holomorphic objects will emerge through the reduction. So you fix a smooth principal bundle. So what that means now is that the same thing I talked about before, you have the same kind of transition functions, but they are now smooth functions. Okay, from the intersections of patches to the group. And the base space, or the base of my cotangent bundle will be the space of affine G-valued 0-1 connections on the principal bundle. So what that means is that on any pair of charts, or on any chart, I have a 0-1 form. Okay, so it's got a component along dz bar only, and it's G-valued. So A here is a G-valued function, and it's a smooth function. Okay. And the fact that it's a connection, what it means is that on different charts, the two different representations of that connection on two different charts, they connect together by a gauge transformation via the transition function. So that's what it means to have a 0-1 connection on the principal bundle. Okay. So why are these relevant for describing holomorphic structures? Is because if you have any such 0-1 form, then it defines a unique holomorphic structure on the principal bundle. So the way to see this is that take this structure, the 0-1 connection. You can always move to a local trivialization. So locally, you can always trivialize the bundle in such a way that this connection becomes 0, identically 0. So you can move to a local trivialization where it's trivial. So these HIs are defined on each patch, and they implement a change of local trivialization to trivial connection in one form. And the point is, once you've trivialized the components of the connection, you see in this equation that that leaves you with just this term. So del bar of the transition functions in that local trivialization must be 0.
Is this like normal coordinates?
Probably, yeah. Well, it's adapted coordinates, I would say, to the holomorphic structure. So the A double prime defines a holomorphic structure because I can always trivialize it away locally. And in that local trivialization, my transition functions are holomorphic. Okay, because I just have del bar equals 0. Okay, so they define, each of these A double primes defines a holomorphic structure. And moreover, if I have two such 0-1 forms, they define isomorphic holomorphic structures if and only if they're related by a bundle automorphism, meaning a global gauge transformation acting on every patch. So the slightly confusing thing is that there are 3 different notions of gauge transformations. There's a gauge transformations across patches. There's a gauge transformation on each patch, which implements a local trivialization. And there's a gauge transformation also on each patch, but which satisfies suitable compatibility conditions on patches. So these G's are not the same thing as these H's. So it takes a while to get accustomed to this framework, but it's sort of, it's a natural setting for the Hitchin system. Okay. So, you know, as a physicist, you recognize these 3 equations are the same, but they represent fundamentally different things. Okay. So now the point is, I want to start with the cotangent bundle of this affine space of connections. And I want to, because if 2 connections are related by gauge transformations, they represent the same holomorphic structure. I want to gauge by this action of the group G. So in other words, I want to quotient out by the action of this group of bundle automorphisms on the manifold M. But
Sorry,
yeah.
go on. In the previous slide, you
Yeah.
have the trivialization, which
Yeah.
tells you that locally, the transition functions are homomorphic.
Yeah.
Don't you also need like some additional condition to patch all these trivializations together?
no, if locally you can bring a double prime to 0, then by design the holomorphic the transition functions become holomorphic in that local trivialization. A local trivialization is in every open you just choose you move to a different trivialization, so you change how you represent the fiber by g-valued functions, and that's implemented locally by an HI on each patch. And you can do that consistently across each patch by you have an a double prime and you solve this equation that this is equal to 0. So you solve a double prime equals h inverse del by h. You can solve that locally on every patch. That gives you the change of trivialization so that on any patch the holomorphic structure is 0, or the a double prime is 0. There's no. That's why I said it's different to this kind of gauge transformation where the g's are required to satisfy the compatibility condition that the gi is equal to gij, gj, gj, gij inverse.
Right.
So
Okay. Yeah.
an automorphism of the bundle is such a thing where they patch together nicely, so they define a global transformation. The changes of trivialization are just local things.
Okay.
Yeah, this is a key point because it's not the way things are usually done in 4D transforms. Yeah.
Can I ask another question? So in integrable systems, we're often interested in meromorphic connections that have singularities somewhere on this.
Yeah. So here I'm dealing with genus G greater than 2, and so I don't need to add extra poles, or I don't need to add extra mark points where the lax connection will have poles. All my lax connections in this setting, I'm following in this talk, will be holomorphic. And you can do that on high genus Riemann surfaces. You can have lax connections with no poles.
I see. Is it possible to easily say how this would change if you were to?
Yeah, I'll say that in the end. I'll tell you the result. Yeah, yeah. But the reason, one simplification is that I don't need to add poles. That's the point. Okay. So yeah, we have an action of this group of automorphisms on the 0-1 connections by gauge transformations, and the point is it lives to a Hamiltonian action on the cotangent bundle. So this is really an infinite dimensional cotangent bundle of these 0-1 connections on my principal bundle. And the moment map of this Hamiltonian action is given by this famous Hitchin moment map. So you take a point in the cotangent bundle, which is the fiber, which I call B, because it will become the B field of the Hitchin system of the 3D BF theory, and A double prime is this 0-1 connection. So this moment map, if you evaluate it at this point, it gives you an element of the dual of the Lie algebra. So if I feed it an element of the Lie algebra, I get a number, which is this integral. Okay, so this is a formula to keep in mind. The moment map is the pairing of the B field, which is G star valued, with a covariant derivative of the Lie algebra element, which is G valued. So let me tell you a bit more about this notation. So A double prime here is a 0-1 connection, as we just saw. The coordinate on the fiber is this smooth Higgs field, which is described as the Higgs field before, but now it's a 1-0 smooth form, and it transforms under the coadjoint action. So it's the same thing as what I described before as B whole, but now they're smooth objects. Okay. The Lie algebra of this group of bundle automorphisms is just described locally by G-valued functions on each patch, which connect together by the adjoint action. Okay, so this is a way of representing Lie algebra elements of this bundle automorphism. And then you take the covariant derivative of this thing that transforms by the adjoint action, it still transforms as in the adjoint action. So now the nice thing is that because this covariant derivative is a 0-1 form valued in G, transforming in the adjoint action, and the Higgs field was a 1-0 form, transforming under the coadjoint action, they pair naturally to give a global section on the base. And so this is a well-defined object. Okay. So that's the moment map. And if you do the symplectic reduction by this moment map of this giant infinite dimensional phase space, you get back the Hitchin phase space. That's the key takeaway. Okay. So a nice way of describing a Hitchin phase space is as a symplectic reduction of this somewhat easier to describe symplectic structure on the cotangent bundle of this larger space by this particular moment map. Okay. So now the thing is, because we've moved away from the holomorphic setting, the Hitchin fibration, which was this map that describes the Hamiltonians of the Hitchin system, it has to be suitably adapted. Because remember what the Hitchin fibration was. So you took a holomorphic Higgs field and you just plugged it into the different homogeneous polynomials on the Lie algebra. So that gave you some sections of some holomorphic bundles, which was a finite dimensional space of sections. But now we're dealing with smooth things. So now we have a smooth B field. And so if you plug this smooth B field into these polynomials, you get back some smooth sections. And there's no way of expanding it in this basis of holomorphic differentials. So you need some other prescription. So you have these smooth sections of these powers of this line bundle, the canonical line bundle. And what we do is we just take as many points as we need. So n number of points, because we need n different Hamiltonians. So we pick n points on the curve, which are these points. So they're labeled by pairs of numbers. So 1 to the rank labels the polynomial. And then for each polynomial, we pick that many points, dr plus 1. So that's the total number of points, which adds up, as we saw before, to the total dimension of the base. So with this choice of points, I can now define n Hamiltonians, which notice is not enough to define an integrable system on T star m, because T star m is infinite dimensional. I'm just defining n different Hamiltonians on this, which will become the Hitchin Hamiltonians after the reduction. Okay, so the way I define them is I just evaluate the smooth Higgs field at those particular points, and I plug it into the polynomials P. So this defines for me a collection of n different Hamiltonians. And I define a Lagrangian, so some dynamics on the cotangent bundle T star m, by taking the canonical PDQ Lagrangian one form and subtracting the Hamiltonians to describe the flows. Okay, so this is the canonical PDQ minus Hamiltonians. Okay, Lagrangian one form. So remember that in this Lagrangian setting, what we want to describe is dependence of the dynamical variables, which are here B and A double prime, on n different times. So I want to think of an immersion of this multi-time space into the cotangent bundle. So this is just parameterizing my fields A and B double prime in terms of n different coordinates. Okay, and when I pull back the Lagrangian to this multi-time space, I get this Lagrangian here. So B, and then Durand differential of A double prime minus the Hamiltonians with Durand differential of TIs. Okay, so this is a Lagrangian one form again, and I want to describe an action, so I need to pull it back to a curve in Rn. Yeah.
Sorry, Benoit, on the previous step, I thought you said this B, when you take this polynomial, you're getting many form components, but now you're only integrating it over a surface.
So these are, so once I get smooth sections when I plug in the B's into the polynomials, but then I evaluate these at particular points, right? So that this is not in the integral, if that's what you're asking. The integral is only this term.
Oh, okay.
Yeah, I would put brackets if there was an integral. Yeah.
Okay.
So this last term is not integrated. Okay. Yeah. Okay. Good. So now let me describe this symplectic reduction. As we saw, that the Hitchin phase space is a symplectic reduction of this T star m. So the point is that the Hamiltonians that I've introduced there, they are G invariant. So they're invariant under the bundle automorphisms, which act on the Higgs field by conjugation. And the reason they're invariant is because I chose the polynomials to be adjoint invariant. So I can gauge the action as we did before. The general procedure I talked about in this finite dimensional setting, it goes through in this infinite dimensional setting. So I take my original Lagrangian one form, I add to it the moment map of the Hitchin system times Lagrange multiplier, which is valued in G now. Okay. So remember that before it was a one form on Rn valued in the Lie algebra. Now it's a one form on C cross Rn valued in the Lie algebra, because my Lie algebra now is actually functions from C to G. So there's an extra C dependent of the one form. So it's a one form on Rn valued in the Lie algebra of this gigantic group, which are themselves functions from C to the Lie algebra G. So I can describe the one form as a one form on C cross Rn valued in G. Okay, so if I do this, if I have this term, and I remember that sigma star L is made up of these two pieces. The first term, which is an integral over C, combines nicely with the moment map term. So these two terms combine to form precisely the BF action. Okay, so I get the BF action plus these Hamiltonians. Okay, so the BF action emerges in this way by the gauging procedure, which takes you from this large infinite dimensional phase space to the phase space of the Hitchin system. So essentially, this tells you that the BF action is, by design, a Lagrangian. It's a Lagrange. Yeah, it describes a variational formulation of the Hitchin system. Okay. And more precisely here, this is a multiform version, because I'm really, as I described for you, this setting where I have a Lagrangian one form on a multi-time space, which I pull back to a curve. This describes a family of actions which encodes a multi-time version of the 3D mixed BF action. So it really encodes all the time flows of the Hitchin system in one action. Okay. So to really go back to the Hitchin system, we need to go back from this smooth description of the Hitchin system in terms of holomorphic rings. So how much time do I have? 10 minutes?
14 minutes.
Okay. So so I want to pass to a holomorphic description, an actual holomorphic description of holomorphic bundles, rather than using smooth things. So the key is to realize that, in fact, you can describe a holomorphic principal bundle using just two patches. So you can pick a point P on the curve and a small open neighborhood around this point, and then you take the complementary open to be the curve minus that point. And the nice thing is that relative to such a cover, you can always locally trivialize the holomorphic structure on this cover. Okay? So that means that I can always go to a local trivialization where A double prime is 0 on these patches. Okay, so in such a local trivialization where the representatives of A double prime are 0 on both patches, the transition functions, as I showed you before, become holomorphic, and I call it gamma. So the new thing here is that these are holomorphic functions along the curve, but they also depend on Rn. There's an extra Rn dependence that came in because everything is like infinite dimensional. The Lie algebra was really functions from C to G, and this Rn dependence came in through this gauging procedure. Okay, so there's this extra Rn dependence, but they're holomorphic along the curve. So del bar of gamma is 0. What I also need to do is solve this constraint, because I also want the Higgs field to be holomorphic. So I need to solve the moment map constraint. So set it to 0 explicitly. And all that tells me is that the covariant derivative of B is 0, or in other words, because A double prime is now 0, this just tells me that del bar of B is 0. So B is now a holomorphic Higgs field. So it satisfies this del bar equals 0 condition. From now on, I'll always implicitly identify the dual of the Lie algebra G with itself. And this allows me to think of this holomorphic Higgs field as a lax connection. So it's Lie algebra valued now, and it transforms over different patches. As the Higgs field transformed under co-adjoint representation, this transformed under the adjoint representation because I've identified G with its field. So this will be the lax matrix of the Hitchin system. It's a holomorphic function, G-valued holomorphic function on the little patch U0 and on the curve minus a point, which on the overlap connect together by this gauge transformation by this holomorphic transition function. Okay, so this is the data of a lax matrix in the Hitchin system on an arbitrary curve. So the key result is that the 3D mixed BF action, which, as I told you, was motivated by constructing a Lagrangian for the Hitchin system, it reduces in this holomorphic presentation. So if I restrict all my data to be described by holomorphic things, so rather than taking a smooth bundle, an A double prime, which is a smooth 0 in connection, and a smooth Higgs field, I go to this holomorphic presentation. When my bundle becomes holomorphic, it's described by holomorphic transition function gamma on the intersection of the two patches, and a holomorphic Higgs field, which I call L. Okay, so in terms of this holomorphic data, the action becomes this Lagrangian one-form action. So this is a very non-trivial step. You can see this because here there was no mention of transition functions. Just A lives on different patches, B lives on different patches, and they're connected together in some way. This is the BF action. But here you see the transition functions between patches emerging, which is not expected if you just ask, how does this look like in holomorphic trivialization? So there's a non-trivial step happening here. And the action you come out with is essentially PEDQ, and this is the answer to your question, and this is the symplectic structure on the Hitchin system. So on the Hitchin phase space, the actual holomorphic Hitchin phase space, gamma describes the bundle on the base, L describes the fiber, okay? And that's the symplectic structure. It's some integral over a curve which goes around the point P, so it's non-trivial to describe, but that's the canonical symplectic structure on, or rather the symplectic structure is del of this. This is the Liouville one form. Okay. So this is the action we ended up with, which you sort of could have guessed from the beginning because it's just PDQ minus the Hamiltonians, but it comes from this intermediate step, which is the BF theory. So we started with wanting to describe the Hitchin system. We went to this BF action that was a natural candidate for the Lagrangian describing that system. And then bypassing to this holomorphic description, so really taking the quotient fully, we ended up with this Lagrangian one-form for the Hitchin system. So the equations of motion for this action are actually quite subtle to derive. So because there are various constraints between L and gamma, remember L and gamma are connected through this constraint. So it's a non-trivial result to derive the equations of motion. So you vary the action with respect to all the variables L, gamma, and T, with the constraints that L and gamma are connected through this transition function. Yeah. So the equations of motion for L are essentially the existence of some matrices or G-valued matrices M, M0I and M1I on the different patches. These are meromorphic they have singularities at the points Qi, which were the points we chose to define the Hamiltonian. So the M's acquire poles at those points. Okay, but L itself is still holomorphic on the two patches. And so the equations of motion for gamma are the usual Lax matrix equations. So they are defined on both patches. So in fact, you derive this one on the patch U0, but because of the way the M's were defined and connected through different patches, in fact, you can construct the equivalent Lax representation on the other patch. So this other one just follows from this Lax equation and this relation, and the fact that the L's connect in this way across patches. And then crucially, as before, when you vary with respect to the times, you get the involution property of the Hamiltonian. And then here is where stability comes in. Stability was a crucial assumption I swept under the rug, but it implies this very fundamental property of the Lax formalism that these MIs, in fact, described a flat connection on the multi-time space. So this is a fundamental property of these Lax matrices. They're called of the Lax equation. But this comes out from the crucial assumption of stability. Okay, if you're interested, there's more about this in our paper, or you can ask. So this is really a Lax description of the Hitchin system in terms of holomorphic means. The Lax connection described by L0, L1 on different patches connected through the transition function. Okay.
But I think also this has positive definiteness.
Positive definiteness.
And stability under fluctuations, or just
stability in the usual sense of algebraic geometry. Stability of the bundle. Is that what you're asking? Or stability?
If it has,
it's not stability in the sense.
Stability of fluctuations.
It's not stability in the physical sense of fluctuating solution. No, it's stability in a very technical sense. Yeah. Okay, so let me conclude. So what I outlined was the procedure in our paper, which was to derive a Lagrangian one-form for the Hitchin system. We started with this canonical action on the cotangent bundle of the 0-1 connection, smooth 0-1 connections on the principal bundle. So this giant infinite dimensional phase space T star M. The action was really B del A double prime, which is PDQ minus some Hamiltonian. Then after the gauging procedure, so implementing the symplectic reduction of this phase space by the action of the bundle automorphisms to the level 0 moment map, we ended up with a 3D BF action. Okay, and then this was still described in terms of smooth data. So the Higgs field B is smooth and the connection A double prime is also smooth. But by moving to an equivalent description of the this Hitchin phase space in terms of actual holomorphic data, we get an action which was this 1D action I showed you before, which describes the actual Hitchin dynamics on this cotangent bundle of holomorphic bundles with holomorphic structures described explicitly. So I think it was Lewis who asked the generalization to the case with marked points. So this we need to do for genus 0 and 1. If the curve has genus 0 and 1, you don't have enough. The bundle here, or the space of bundles is too trivial. So we need to add marked points to get non-trivial Lax connections, Lax matrices. So we add some marked points, and what we do is we extend the phase space at these marked points by adding co-adjoint orbits of the action of the group G at those points on the curve. So this is the group of automorphisms, which is basically G-valued functions on the curve. And at every point, you get a group which acts on the fiber at that point. And these are just co-adjoint orbits attached to these points, and you have an action of the finite dimensional group on those points. Okay, so these are just co-adjoint orbits of the finite dimensional Lie group, capital G. And what it does, what this whole procedure does when you include these extra marked points is you just get an extra term in the action. So these are, as I said, describing the dynamics of degrees of freedom which are attached to those additional marked points. Okay, so these are just additional co-adjoint orbits attached to those points. So what's really nice is that we have two kinds of objects, two kinds of degrees of freedom. There's the points which are, or the dynamical degrees of freedom attached to the marked points, which is a usual thing we see in the 4D Chern-Simons story. Do you have boundary conditions of those points, or it's probably more like the order defect story where you add marked points, and then at those marked points, you have degrees of freedom which are coupled to the bulk field. Okay. But now, the nice thing about high genus is that you have extra degrees of freedom which are living on the moduli of the bundle itself. So the holomorphic transition function is part of the dynamical degrees of freedom of the Hitchin system. So in higher genus, in particular, you can completely ignore this red bit, and you just have the degrees of freedom of the bundle itself. The bundle is dynamical, and this is just this extra canonical degrees of freedom associated to the bundle. Okay, so we see these two types of degrees of freedom. So we did a few examples in low genus, genus 0 and 1, where these extra mark points are crucial. So with genus 0, we get the rational Godin model. With genus 1, we get the elliptic Godin model. And as a special case, also the elliptic spin Calogero model. So this was all known, but we derive it in this. And there was no known action for the elliptic Godin model. This is new, a Lagrangian formulation of this. And this is the completely integrable elliptic Godin model. So it describes all the times of the hierarchy. So I think Vincent might talk a bit about this example, or he'll discuss it from a different perspective from the R matrix. Yeah. Okay. So some outlook. Once we have an action functional, the natural question is, can you use path integral quantization to quantize it? And now I'm really talking about path integral quantization of a completely integrable system, because the action function, which is this Lagrangian monoform, describes all the time flows of the hierarchy, and it requires developing a new procedure for actually understanding what path integration means for this kind of Lagrangian. There are possible generalizations of the Hitchin system. So the Hitchin system doesn't describe all finite dimensional systems, but there are generalizations of it, which the question is, what is the natural analog of the 3dBF theory for those generalizations? And then a very interesting question, which Lewis alluded to, is what happens when you go to higher dimensions? So this was all finite dimensional, little n was a finite number. If you increase the dimension to infinity, so the question is, can we similarly derive multiform versions of the 4D, 5D, 6D, and so on Chern-Simons actions? Do these describe Lagrangian 2-3 form formulations of the corresponding integrable hierarchies? So we're now talking about the entire hierarchy. And can we play a similar game in high genus? So somehow in this three-dimensional setting, dealing with high genus was technically difficult, but quite doable. And there's a lot of people have been thinking about high genus, in particular, Masahito in the original paper with Costello did general genus. But I want to understand if it's related to this approach we've been following of thinking about holomorphic structures on principal bundles and doing some sort of reduction procedure. Okay, lots of other questions, but I'll end here.
Thank you very much. Opening remark.
maybe a technical question. So you're looking always here at the implementation at the origin, pre-image of
Yeah.
zero.
Yeah.
But of course, you can take the pre-image of some other
Yeah.
final point. That understand what that does.
We haven't done that because the Hitchin system is the one reduced at zero. It's a very good question. What happens? So this is the kind of generalization that you can play with. What happens if you move away from this setting that gives you Hitchin? Do you get something positive?
Quite nice.
Yeah.
Information.
Yeah, maybe they give deformations. Exactly. There'll be a parameter which is the level you reduce at. That might be a deformation parameter of the Hitchin system. That's the kind of generalization you could play with. Yeah.
More?
A very stupid question. Why do you call this mixed BF theory?
Because it's topological along R and holomorphic along C.
Okay.
I guess for each ensign is called semi-holomorphic because there are two topological, two holomorphic direction, or one if you count complex dimension.
Like
I think that's why it's called mixed.
Right, but the 3D BF theory that I've seen typically
Yeah.
is that it has a BQ term.
Are you sure? I've not seen that one. But there are, I think this one is probably called mixed to distinguish it with maybe the one you have seen.
Yeah, it's just that like it's
So-
just topological homomorphic, and then you just
Yeah.
make BF plus BQ topological homomorphic.
Yeah, but B would not be a 1-0 form in that case because B cube wouldn't
Yeah,
make sense.
that's true. Yeah.
So yeah, I think with the B cube term, it's not the same theory because
No,
B is
it's
not a
not.
1-0 form.
So the okay.
Yes.
You described, even for a very high genus surface, you described it with just two patches, and so generically this other patch will actually have like non-contractible cycles in it and stuff.
Yeah,
did you
but
say-
so it's a very deep result about holomorphic principal bundles that you can always, every holomorphic principal bundle on a non-compact Riemann surface is trivial, holomorphically trivial. So it's a non-trivial fact. There are non-trivial cycles, but the holomorphic bundle is trivializable over that Riemann surface because you remove one point, so it's non-compact.
So should I think that I just don't have any winding modes, or should I think that this gamma somehow captures all of the winding?
Yeah, so you can actually, there's a way of thinking about how gamma encodes all the moduli of the curve.
Yeah.
In one transition function on that small patch. Yeah. Yeah, Rick, I can explain a bit.
Yeah, thank you.
Yes.
Uh,
Last question.
Yeah, so just partly a comment as well. So the ramified case when one tries to understand Hitchin systems from for n equals to force for Young's theory, which is twisted, that the ramification comes in through disorders surface defects, which are called Gukov-Witten defects.
Yeah.
So I'm tempted to think whether ramification in this case could also somehow involve disorder defect.
Possibly, yeah. I mean, I think you need to tell me how this works. But so the reason I said it looks like disorder defects is because you just choose some marked points at which you add degrees of freedom and you couple them to the bulk field. This action without this term, we derived it earlier in some earlier with a former student of mine, Jenny Winstone, and you do see this kind of defect, order defect term where you have D plus the connection A, and then when you go to the gauge where the connection is 0, it becomes this term. So there is this natural term you can write down, which looks a lot like the type, the ordered type defects that Costillion was actually.
The type A defect.
These are type A defects, yes, but they look a lot like the kind of order defects that Costillion has write for each ensign. Because sorry.
I suggest more questions during the break. So let's thank Benoit again.